We are joined by Shahryar Garamanian. We're going to be talking about electrifying heating with heat pumps in commercial buildings. I'm very excited for today's session. Before we get started, just a few things to note. We are recording the session. Both the recording and the presentation materials will be made available to participants. Available on the Save on Energy website in 1 to 2 weeks. And we'll put some links in the chat for you to bookmark and look out for those things later on. We do typically mute the audience while we go just to eliminate background noise, but we also encourage active participation. So if you have questions, there's a raise your hand feature. You can use the chat or the little Q&A box. My name is Megan Murray. I'm with CIT, and I'm going to be facilitating the session today. And like I said, we're joined by Shahryar, who is our subject matter expert and is going to take us through the materials. So with that, I will hand it over.
Yeah. Thank you so much, Megan, and welcome and good morning, everyone, to this session, actually. My name, as Megan said, my name is Shahryar Garamanian. I'm a mechanical engineer I would say, by education and by profession as well. I worked in a different industries. I worked in a different continents as well, in Middle East, in Europe, and in North America as well. And my previous life was with the government of Ontario, from Infrastructure Ontario. So I was with the government, and then doing the energy and sustainability projects with them actually. So today session, as Megan said, is about electrifying the heating system of a commercial building by the heat pumps. That's the goal of today actually, and we want to go through this, and we want to see that what are the opportunities actually. So we want to explore what is a heat pump technology. So just a very brief and basic review of that one, and then exploring some typical retrofit opportunities for commercial buildings actually, and then exploring some technical and financial potentials about these, and then key concepts about when you want to develop a business case about this one. So that's an overall agenda for today actually. And as Megan said, I love to have active participation, and then receiving questions and answering, and then talking about these topic actually together. So if you have any questions, either type it in a Q&A, and then Megan will announce it, so then we can go through that one. Or if you like, so just unmute yourself and then ask your question, so then we can pause and then we can talk about that one as well. So without further ado, let's start with this basic question, is that why we are going to have a HVAC system in our building, why we are going to have a heating, cooling, and ventilation and air conditioning in our building actually. So the main reason, the first of all, and the main reason is the health and safety and well-being, because we need to provide air quality. We live in a cold climate more than 6 months of a year, I would say. We are inside in indoor environment actually, so we need the fresh air, we need oxygen to breathe. So that's why the air quality and ventilation becomes important. The other one is a temperature regulation, because we are humans. I mean, we have a limited temperature which we are comfortable with. So that's why, again, we need the heating and cooling systems to provide us that comfort. And at the same time, the humidity also becomes an issue again when we cool down sometimes. So we need maybe remove humidity as well, or also during the winter season, maybe when we heat up, we need to add humidity to the buildings actually. So then these are the reasons that we do heating, cooling, and ventilation and air conditioning basically inside our building actually. I want to touch on this basic thing as well, is that to compare air, water, and refrigerant, from an engineering perspective. If you look at air, I mean, most of our HVAC system, they use air in North America, I would say. When I worked in Europe, I mean, it's different. They have a dedicated outdoor air units, dedicated outdoor air for ventilation, actually. So DOA systems, those are the ones that they just provide ventilation, and heating and cooling is done by water or refrigerants actually. On that note, air has the lowest thermal conductivity and lowest specific heat capacity. And then, because of this, we need a larger ductwork or air handling units actually to transfer the same amount of heat compared to the water and refrigerant. Temperatures also can vary depending on the outdoor conditions. If we are talking about air source heat pumps, so then the air source heat pump become dependent on the outdoor weather. So then again, extracting heat from outdoor air sometimes maybe becomes a challenge, or also from the inside dump it to the outside as well. And then, forced air heating and cooling system, that's a very common one. Comparing to air, we can use water actually, like a hydronic system. They can actually carry a larger HVAC loads actually, and the reason is that the water have a higher thermal conductivity and a specific heat capacity, and because of this, we need only smaller piping actually to transfer the same amount of heat. Maybe I can touch on this one. If you have an 80 kilowatt heating or cooling system with a temperature difference of only 2 degrees Celsius, for if we want to transfer that 80 kilowatt, we need almost 33,000 liter per second of air to be moved. But in comparison, we need only 11 liters of water actually. So the reason is that because the specific heat of water is 4 times more than a specific heat of air, and also thermal conductivity of water again is 25 times more than thermal conductivity of air actually. The same idea is applying for refrigerant. Refrigerants are more efficient than the water. So I wanted to remind you that we have these systems, and basically our heat pumps actually are using a refrigerant inside. And that's why one of the reasons that the heat pumps are more energy efficient is because they use these refrigerants, and because of a higher specific heat and also higher thermal conductivity actually. Uh, and that is the reason is that the heat pumps are, less energy input actually that we require, and they are better for the temperature controls. But let's jump into the heat pumps and see that what is a heat pump. In a very simple word, heat pump is a machine, is an equipment that it can transfer heat from one location to another location. So that's a very simple definition of a heat pump actually. So heat pumps, the good thing is that they are energy efficient and they are highly efficient. One of the reasons is that because they use a refrigerant inside, which means that they can carry a lot of heat with themselves and then dump it somewhere or extract it from somewhere else. The other good thing is that the heat pumps, they can be used both for heating and cooling purposes. So if this is on the left hand side, we are talking about the cooling. What is happening is that we want to remove the heat from indoor of our buildings actually to outdoor. So the direction of the heat flow that is done by this machine, which we call it heat pump, is going to be in this direction. In a winter season, it's going to be the opposite, which means that we are going to take the heat from outside actually, and dump it to the indoor. And that's why we have reversing the cycle. And thanks to this reversing valve that exists, this is one extra component that exists within the heat pumps that air conditioning systems, they don't have them, is this reversing valve. This reversing valve can switch the outdoor unit and indoor unit, and then they can become a condenser and evaporator based on the season or based on the operation that we want to have. So the good reason again to use a heat pump is that because they are efficient, because we can use them both for heating and cooling purposes actually, these are the first reasons that we need to consider the heat pumps actually. Before jumping to that one, the other components that of a heat pump is typical is like a compressor that we have, and an indoor coil or heat exchanger, and an outdoor coil or heat exchanger. And these are, and we have an expansion device actually. So these are typical equipments that exist inside an air conditioning, but the only difference is the reversing valve that I wanted to touch on that one. But let's look at the ideal case actually, which never we are going to achieve this one, but this is from engineering perspective. From an engineering perspective, if we have a building actually, and this building actually requires a, 80,000 kilojoule per hour, or almost 22 kilowatts of heat actually, to maintain indoor temperature at 20 degrees Celsius while the outdoor temperature is -2 degrees Celsius based on a reversible heat pump engineering calculation, we are going to see a COP or a coefficient of performance of 13 actually. I will define and show you COP later on, but this is an efficiency of a heat pump. So the ideal efficiency of a heat pump is 13 actually in this situation between these two temperature, 20 inside and -2 outside actually. And the power consumption for these 80,000 kilojoule per hour that we require, it becomes almost 2 kilowatts. So basically what I'm saying is that in a very ideal case, which unfortunately humans we cannot achieve, if we put an air dryer, a hair dryer actually inside the building, that can heat up the entire building actually. But we don't have that machine that has this efficiency, unfortunately, and this is the ideal, situation based on thermodynamics and engineering. But let's jump into the reality. So for the same case, actually, in the reality, if the building requires these 22 kilowatt, or which is equal to 6.3 tons of heating, actually, we can put baseboard resistance heaters actually, and the resistance heaters, they are 100% efficient basically. So means that we have to supply 22 kilowatts of heating actually. If we are going to install a natural gas boiler or furnace, let's assume with the efficiency of 85%, then we need to provide 94,000 kilojoule per hour, which is almost 26 kilowatts. So if we have a, sorry, I mean, it's hard with writing with this. So it's going to be 26 kilowatt that is needed if we want to have a natural gas burning system with 85% efficiency. But let's compare that one with a heat pump. Let's assume that we have a heat pump that its COP or coefficient of performance is 2.5. This means that we are going to only install a 9 kilowatt actually heat pump for this building, and that would be enough actually. So this is great. A 9 only kilowatt a heat pump can provide the same amount of 22 kilowatt that the building is needed versus the natural gas, which was 26 kilowatt, or a resistance heater, which going to be 22 kilowatt. So this is the reason is the heat pump is more efficient to be used actually inside our building. I didn't touch on the greenhouse gas reduction because now we are switching from natural gas burning or fossil fuel burning system to an electric one. And the good thing is that in Ontario, we have a green building, green electricity actually generated. So it's great to use that one. But I didn't touch on that one. This is just a pure engineering, and it shows that why the heat pumps are more efficient and why we need to consider the heat pumps for our facilities that we are running. But let's jump into some jargons and some metrics that the heat pumps can be compared with actually. So in the first, I have two steady state efficiency terminology. So one of them is the coefficient of performance, which is basically is the amount of heat that delivered by the heat pump. It depends on the season that we are talking. If it's a heating season, means that how much heat was brought to the building, and in the cooling season is that this heat is how much heat we extracted from the building, divided by the amount of electricity that provided to the heat pump. So basically, this can be in a term, in a units of BTU per hour, kilowatt hour, or any other, units that we wanted. So this is the COP. The COP based on the AHRI, the Air Conditioning, Heating, and Refrigeration Institute, is getting measured at 8 degrees Celsius outdoor temperature and -8 degrees Celsius. So when you see COP, you see only two steady state COP. But in reality, the outdoor temperature varies all the time. So then the COP changes actually. So we need to remember that this COP is in a steady state efficiency of the heat pump actually. Typically, for a heat pump of 1 kilowatt of electric energy, it can transfer up to 3 kilowatts, similar to the example that I showed you, which means that 2.5 to 3 times more heat transfer, and that's why it makes them more efficient. The other metric, again, which is in a steady state, similar to COP, is the energy efficiency ratio, or EER. These are also uh, published or actually shown in a spec sheet of a heat pump by the manufacturer. And EER basically is just looking at the cooling capacity. It means that how much cooling is provided at this temperature, 35 degrees Celsius or 95 degree Fahrenheit, divided by the amount of electricity that is actually input to the heat pump actually. And then an EER, can go from 6, 12, or they can be lower than that one as well. So it's better that we look at the EER and COP at the same time. But again, COP is going to have one COP for heating, one COP for cooling. On the other side of it, we have the seasonal performance factor. So one of them is the heating seasonal performance factor, or HSPF actually, which is this is the total heating that is required actually during the entire heating season or winter season, divided by the total electricity that was given to the heat pump actually. And then this graph shows actually how much saving we can have. So if we have a heat pump with a heating seasonal performance factor of 12, then 76% saving we can achieve with that one. But we can have a lower HSPF, which is going to be like a 6.8 or 7, which they don't provide that much, saving compared to other heat pumps. So we should be careful. This is a comparison of two heat pumps with each other, not comparing with the natural gas, burning systems actually. The other seasonal efficiency factor is a seasonal energy efficiency ratio. Again, this one deals with the total cooling that is needed or output to the basically to the building, divided by the total electrical input to the building. This is again a seasonal, which means that it considered the entire season operation actually. So again, we have a CER of 13 to 15, and then it can go up to 20 to 24 actually, which they are the best to be considered. So when you want to select a heat pump, it's better that you look at all these four metrics actually. All of them, two of them are for seasonal, two of them are steady state situations, and then see that which of them makes better. But we need for sure to do a trade-off, because some of them might be, when they efficiency goes higher, so they become more expensive as well actually. One thing before I jump into the retrofit process, I want to bring your attention to an air to water heat pumps. As I showed you before, waters, they are better than air. If there is a possibility, or if our buildings, they have actually an hydronic system, so they are air to water or water to water heat pumps actually, and then they are good for sustainable commercial buildings like offices, hospitals, schools, and so on actually. They use different technologies. They use electronic vapor injection compressor, and they have a refrigerants with a low global warming potential actually, and they uh, efficiency can be up to 5 times more or better than the boiler chiller convention actually. And the system is like this. So you have an air to water heat pump, and it connects to a what a waterless sorry, a tankless water heater, and then there is an expansion tank, and then the rest of the control systems that we need. So this system, I want to bring your attention that exists in the market these days, so it's good to take advantage of that one. But let's look at, if we want to do a heat pump retrofit, how we should take a look, and what are the steps that we need to go. So let's start from, first of all, from the outdoor unit actually. So we need to first of all think of what sources from outdoor we want to go to use it. First, and the most common one, is the air. So means that we extract heat from air in a winter season, and we dump actually extra heat uh, in from inside of the building in summer season actually, again back to air. So this is a air source heat pumps actually, so we can use that one. But it's good that we consider the ground source heat pumps as well, because the ground source heat pumps are really good, and they are more efficient than air. And one advantage is that the ground source heat pump, they don't need the defrost system. because the ground temperature in the GTA, for example, on the projects that I've worked, is around 8 to 10 degrees Celsius all year round, actually. So if you have a ground loop, so if you have a boreholes, underground, it's gonna be all year around 8 to 10 degrees Celsius. So that's the one thing that first of all we need to consider and see that, okay, for outdoor unit that we want to put, where do we want to put it? Do we want to put it in the air, or we want to have a ground one? The next one is the indoor distribution. So in indoor distribution, we can have air, which is a ducts. We can have the chilled water or the hot water piping system, or we can go to the VRF system and actually bring the refrigerants throughout the building. So this is also the indoor distribution that we needed for our buildings, actually. After deciding about the outdoor unit and also the distribution system that we are going to have or is the best for us inside the building, and I touched on that one, say that refrigerant is the best one because it's highly efficient, and the size of the pipes and everything, it becomes very, very small compared to the ducts of air that we need to do that one. Now it becomes the time for sizing the heating and cooling loads, actually. Now we need to size the heating and cooling loads, actually. And then now this is the time to see that, okay, which type and also, size of the heat pump is it good for us? Depends on the price of the heat pump as well, actually. There are some cases that we need a supplemental heat sources when we want to retrofit to the heat pumps, because we're going to have a balance point. Basically, if this is the heat loss of a building, actually, then the manufacturer will give you a graph, actually, that based on the outdoor temperature, how much is the heat supply of the heat pump. So then this point is going to be the balance point, actually. And anything in here, any extra heating that is required on the left-hand side of this X that you see here, means that we need to provide a supplemental heat sources, actually. So I encourage you, if you have time, just watch the recording for the residential session that we did it last week for ISO, actually. And in there, actually, we have a details of this, sizing and supplemental heat sources there, actually. Then we go to the efficiency. So I have only one of them, the heating, because the most important one for our facilities. We live in cold climate, but please check the COP, please check the EER, and please check the SEER as well. So please check all four efficiency metrics of the heat pumps and decide that which of them the best. If you select an air source heat pump, which means that outdoor unit is going to be sitting outside, then the defrost becomes an important factor, actually, especially for commercial buildings. I worked in a project for installing heat pumps in Thunder Bay, actually. And the good thing is that because of avoiding the defrost, because of avoiding any snow or ice accumulation and better defrost, actually, and helping the heat pump, we decided to install the heat pump inside the mechanical room, which was in the penthouse, actually. And then we had some grills, in front of it. So then it was a great performance that we saw. But the heat pumps during the heating season, they need to do the defrost, actually. During this time, the heat pump is working, but they don't supply any heating, actually, to the building. So we need to consider that one, and that is why that the location of the installation of the heat pumps becomes important. It's not like the air conditioning system that we put everywhere that we want, and then we say that, okay, that's enough because we cover them during the winter. But these machines, they need to run during the winter season, so they need to be above the snow level, actually. So we cannot put them right on the ground. So they need to be above the snow level. And also, if we can have an enclosed area around it, that also helps them, to perform better and improve their efficiency. And then we go, we need to consider the maintenance, how we want to maintain them, how we want to clean them and check the refrigerant and the performance as well, actually. These are the typical steps that if we want to do a retrofit, and considering heat pumps for our facilities, we need to go step by step and think, from the basic questions that, what outdoor source that we want to use up to the maintenance. But for sure, there is a parallel trade-off of the cost of the system as well, that we need to run a life cycle cost analysis and to see that which one makes more affordable or make more sense for our facilities actually. Now let's look at the types of heat pumps. The heat pumps, as I said, it can be air source heat pump, uh, or it can be ground source heat pump. There are water source heat pumps, but I didn't see that much in Canada to be used. But there are also good opportunities in US. There are many places that they use. So if we have a lake, or if the codes and if the municipality allows us actually water source heat pumps, they can be similar to the ground one, which means that we dig in the ground, but we are connecting to a water actually underground source, and then we use for our heat pumps. The other heat pump type is a hybrid heat pumps actually, and then the last one is absorption heat pump. Absorption heat pumps for commercial buildings, which require at the same time heating and cooling, or for the buildings that they provide or they have access to low quality heating sources like the processes or anything else, absorption might be a good option for them actually. The common commercial heat pumps are like this, the single split. I'm sure that most of us saw these ones for the IT room, for example, which they wanted, an independent, cooling system, or for elevator room, for example. So then these are single split systems. Then we go to the multi-split systems that, again, these are also another common commercial heat pumps. And then we go to the package terminal heat pumps, which is a one unit, and then mainly in the hotel rooms that we saw them, it has everything inside. We need to just cut the wall and then put it there, and then add a grill on the outside, and then that's it. It has everything inside: the fan coil, the heating coil, the cooling coil, the reversing, the compressor, everything inside. Or the rooftop units actually. So rooftop units is one of the greatest actually opportunities these days. It's not that expensive actually. So if you have a rooftop unit and it's time to change it, so always consider the rooftop units actually with a heat pump, because they have already an AC inside it. They need to just add a reversing valve to the system, and then basically you get a rooftop unit which is actually equipped with a heat pump. Then we go to a very advanced system, which is going to be VRF. Today, I will talk a little bit about that VRF system, or variable refrigerant flow system, which basically we take the refrigerant from the outdoor unit and just bring it to every zone that we wanted. And the last one is a hybrid heat pump systems that is a combined heat pump systems that we bring to the building. So air source heat pump is very common actually. Heat pump, and there are standard and cold climate air source heat pump, or we call them sometimes CCASHPs. These are also available. They can work up to minus 31 degrees Celsius. They are a little bit more expensive than a standard one, but again, they exist and they can operate, at a high COP, let's say 2 to 3 actually during a very cold days actually. So they function, as I said, they transfer heat between indoor and outdoor, depending on the season, and it can be used in a large commercial buildings. They are relatively easy to install, actually, and very inexpensive installation, and having them for the buildings. Actually, the only disadvantages is that the standard one efficiency actually decreases with extremely cold temperature, and that's the time that we need to actually sometimes to shut down actually the air source heat pump that we have, and then run a backup system, because the heat pump cannot actually bring the heat from outside to inside if we are installing in a standard. But with a cold climate air source heat pump, there is no worries and there is no need to consider supplemental. Typically with a standard uh, uh, air source heat pump that I saw is that when the outdoor temperature reaches to -6 to -10 degrees Celsius, that's a good time with the standard air source heat pump to be turned off, and then using an auxiliary heating system actually. So the air source heat pump are like this. We have, as I said, we have a split system. The split system can be a ductless, which means that we have lines of refrigerant is going from the outdoor unit to an indoor unit actually. Or we can have a multi-zone mini split system. So basically, we have an outdoor unit, and that outdoor unit can be connected to anything, can be connected to a ceiling cassette, can be connected to a ducted, system, or a fan coil, or whatever system that we have. The other air source heat pump is the exhaust air heat pumps. I will show you this one. This is an interesting heat recovery system. That's a really good one. Then the packaged one, and then we have a reverse cycle chillers as well. These are also heat pumps, so this is good also to be considered, and also variable refrigerant flow system actually. So a split system, they have an outdoor unit, they have an indoor unit, and it's very common in a small to medium commercial buildings. They are flexible with installation options, and they can provide both heating and cooling actually, and it's relatively easy to maintain and use them very efficiently. But with these systems, we need to do a duct work, but there are some ductless heads as well that for distribution if we want to do that one, but they become more expensive actually. Then we go to the dockless systems. The dockless systems, again, we have an outdoor unit, and then we need to bring the refrigerant to the indoor unit. And again, they are easy to install. They are high efficient, and they can provide an independent zone control actually. But they are more expensive compared to the other system that I showed you actually. If we have a ducted system, they are less expensive compared to these ductless one actually. Then we can have the same idea with a 1 unit or 2 units, and then multi-zone mini split heat pumps. Again, the same. It provides flexibility with the zoning. Actually, they are energy efficient, and they can customize the comfort, because maybe one zone they want to have a heating, and one zone they want to have a cooling at the same time. So then we can have such a system actually. And then if we have a multiple outdoor units actually, but again, the disadvantage is that it has also a higher initial cost, and also the installation can become complex. So we need an expert to design such a system. But this is good for larger offices and buildings actually, which they require multiple zones with the independent temperature controls actually. Now we go to the exhaust air heat pumps, and these are basically a heat recovery system from the exhaust air. So the exhaust air typically is connected to the roof, and then we just dump it outside actually. But there are many projects that I saw that they install these exhaust air heat pumps actually, and basically they recover the heat from the exhaust air actually. So this is a really good recovery system, and it incorporates the heat pumps as well, and it uses the heat pump mechanism actually to capture the heat basically. So it's really good, and it can operate on exhaust air capture and do the heat exchange actually, and then bring that heat actually either for preheating during the winter season, or for the water heating that if we wanted for the summer season as well. So basically, we are going to utilize the waste heat that the building has it actually, and then it improves the overall building's efficiency actually. It has the only limitation that it has is that the heating capacity, because it depends on the size of the exhaust that we have. So then it can be a limited amount of heating provided. But again, this heat pump is really good to be considered for any energy recovery for our buildings if we have a large amount of exhaust air that going out of our buildings actually. Then we go to the packaged air source heat pumps. So these packaged air source heat pumps, they are good for small commercial buildings, and typically they are going to be installed on the roof. They are compact, they have everything, they are easy to install in a very tight spaces as well. So it reduces the indoor noise because everything goes to the roof actually. But their disadvantages is limited to smaller capacity, and also they are less efficient than the split systems actually. So that's the one thing that we need to consider if we are going to uh, take a look at these packaged air source heat pumps actually. So their efficiency, especially during the heating mode, it becomes really important. But the components is compressors, condenser coils, evaporator coils, and air handler, and the fans, and then thermostat and the control system. So they are good actually. They are, compact design. That's a good one that we can benefit for our project actually. Then we go to the reverse cycle chiller heat pumps actually. Again, these are good for larger buildings with existing hydronic system the distribution. So basically transfer heat to or from a water loop actually, and then, either heats or cools the building actually. So again, similar to that, recovery system that you saw, this is a reverse cycle, chiller heat pump. So these are good also, but the only thing is that we need to have a hydronic infrastructure, and this is a good one. But again, this needs an engineering design. It has, complex installation, and the initial cost compared to the split system can be higher actually. The next one that I want to a little bit expanded on that one is the variable refrigerant flow heat pumps actually. So variable refrigerant flow heat pumps are basically they are similar to air source heat pump, which means that they use outdoor air actually as a source, but inside we, instead of duct for the air or the water pipes for the hydronic system, we just distribute the refrigerant system through the pipes. And the good thing is that these systems, they they are very advanced types of a split system, actually, ductless split systems, and they're good for large commercial buildings, hotels, offices, with a diverse heating and cooling needs. So if one area requires heating and the other area requires cooling, these VRF, they can work in those systems, and they are really good actually. So, for example, in a hotel room, in a hotel tower, one room, one guest requires heating, one guest requires cooling. So then they can both use that actually by connecting to these variable refrigerant flow systems actually. They are high efficient, they are very precise temperature control, and they can provide simultaneous heating and cooling, but they have the highest initial cost and also a complexity in installation, and the maintenance needs to be considered actually for the VRF system. But the VRF systems actually, we can have a different zoning easily done actually, and it's really good for decarbonizing the heating and cooling system. So basically, everything is going to be electrified, similar to other heat pumps, but this is for the entire building. So it lowers the carbon footprint, and this is actually it reduces the overall cost for commercial building owners, because if you look at the life cycle costs of a VRF system compared to a conventional system, you see that the VRF actually is much more affordable if we look at 30 years of operation and installation cost of a VRF system actually. And then we can have a multi-zone system, and then manage those ones actually. The VRF systems, we have two VRF systems. The one VRF is VRF heat pumps. Basically, it means that each unit, for example, let's say this is unit one, and unit one is connected to the outdoor unit number one, actually. And then this person can control the unit one, either heating and cooling. This becomes similar to, ductless split system. And then unit two serving actually the zone two and zone three actually, but the zone two and three, they need to operate in the same mode. For example, in this case, we have both of them on the heating actually. So if one of them was heating and the other one was cooling, then we need to go adding an extra outdoor unit to that actually. So then each of these zones becomes independent. But the good thing is that now we have a technology advancement, and now we have a controller box, which means that we need to install only one outdoor unit, and this outdoor unit is connected to this, branch controller box. And then each of these zone one, two, and three, they can decide what they want. Do they want heating and cooling? They can basically switch whenever that they want actually, and the outdoor unit connected to that, controller box can manage that one actually. So that's the beauty of a heat recovery. This system is called VRF heat recovery heat pumps actually. So this is a good one to be considered for our buildings. But which VRF system is good for a building? Again, depends on, we need to answer these questions. How is the zone layout our building? Do we need simultaneous heating and cooling for a building or not? Is the initial cost determining the factor, which means that between VRF heat recovery, which has the highest initial cost. How about the moisture and relative humidity? How about the ventilation system? Because the VRF, we don't duct the air actually through the building, so we cannot add the fresh air to this heating and cooling system, basically. So we need to consider a dedicated outdoor air system or DOAS system, which most of European countries, they use this system. So they separated ventilation from the heating and cooling. So that's a good one to have that one. And basically, DOAS can control both ventilation or the fresh air that the building occupants they need, and also the moisture control, which is the humidification or dehumidification. The other question is that how is the occupancy schedule in different spaces, and is there a space branch selector box we need it or not? Actually, because that's going to add extra cost to our design, basically. And then where we can put the outdoor unit, actually. So because this is also an important factor, both because of the efficiency of the outdoor unit and also the length of the refrigerant piping that we need to do, actually. And then there are standards, ASHRAE 15 and ASHRAE 34. These are the standards from ASHRAE. I will show you later on. There are other standards that we can use them if we are going to consider a VRF or variable refrigerant flow for our buildings, actually. So the good thing is about the VRF, similar to heat pumps, is that everything is going to be all electric heating and cooling. And in a VRF system, we don't need a supplemental or auxiliary heating system, actually. So that's a good one that we can benefit. And as I said, any ceiling cassette, any horizontal ducted system, any floor mount or wall mount, fan coils, any of them can be connected to the VRF system, and then they can provide heating and cooling for our facilities, actually. If we compare the VRF system with a conventional air conditioning system, so it's good that to take a look at that one in a cooling mode, actually. The black line actually shows that how the air conditioning system that we have, it works, actually. So you see that it goes on and then, off, and then, basically it's short cycle with a higher peaks, actually. But a VRF system, they reaches a set point faster, actually, because they are more efficient and they don't short cycle on a high peaks or low peaks, actually, that much. So this will gives us a minimal temperature fluctuation, which means more comfort for the building occupants. At the same time, is also this means that less energy use for the VRF system, which means that the VRF system becomes a higher efficiency compared to conventional, air conditioning system that we have. So this is another comparison of the VRF with the conventional cooling system. Now let's look at what is inside the ASHRAE and other standards actually mentioning about the building system. So let's look at the office building. So an office building, it depends on the size of the building. It's a high-rise office building or a small to medium-sized office building. So again, depending on the system, we can go with the perimeter, fan power, VAV, actually terminals, or induction or fan coil system, or for a small to medium sized office, we can consider heat pumps, either mini splits or the VRF as well. So we can have these systems, or if the size allows us, so then we can go with a package terminal, air conditioning with a VAV system, or a single zone, constant volume, uh, for example, water source heat pumps as well. So any of these, you know, systems can be considered for an office building. ASHRAE has this nice table, actually, which compare, depending on the size of the building, actually compares different systems, either a VAV, variable air volume, and also a water source heat pump, either is decentralized system or is as a centralized system. So every of them you can see in an ASHRAE, and it helps through the design of that one. So we can consider, as I said, the geothermal ground source heat pump, or we can consider a hybrid ground source heat pumps actually, or a package, single zone or variable volume units. For the light commercial, we can consider split system, or if we can afford, we go with a mini split or variable refrigerant flow units actually. Again, each of them presented in ASHRAE standard actually. So these days, the electrical grid that we have is getting decarbonized thanks to ISO and OPG in Ontario. We have one of the greenest electricity actually in North America, so we are really good. So it's better that we take advantage of that one. So now it's better that we increase our efficiency of our systems. That's a one thing, and also if we can use thermal end uses with a renewable energy, that if it's possible. Again, VRF can help us doing this one, or heat pumps can help us, achieve that decarbonization that on the grid is happening, on the generation and grid distribution transmission is happening. So it's better that we do it on the building side as well, actually. Now let's switch the gear and now let's look at the market for the heat pump. So in US actually and Canada, so basically North America, they expected that the market for the heat pump, it will be almost $11 billion by 2028. So it's going to be a huge market. This was in a study done by Navigant, actually research and support by Mitsubishi. So they presented that, because every building owners, they are now moving toward I would say, a more efficient system, which is like a heat pump or a VRF system. So then the market will expand up to $11 billion actually. In Canada, we see this is a little bit old. This is study published in 2018, but the recent version of this one is available for just residential, not for commercial. But in Canada, the total installed heat pump, the good thing is that you see that in Ontario, which is the yellow color, it's increasing actually, and it's going higher and higher. If we look at the recent study that was done in 2023, last year actually, it showed actually $1.5 billion actually worth, US dollar actually, was the worth of the heat pump market in actually Canada. So, and they actually calculated and they saw almost a 7% annual growth rate for the heat pump market. So it's a huge market now in Canada as well. So it's almost $1.5 billion based on the study that was done last year, and it's growing 7% every year actually. So, and the thing is that mostly in the previous years, the residential sector, they considered actually to install heat pumps, and the commercial sector, they were, almost a third of that actually. But now the market is changing and the commercial sector actually is coming, and the commercial sector is considering to install heat pumps or variable refrigerant flow for their facilities actually. So uh, the electrification is happening across the North American, I would say market actually. So basically, in this slide on the left-hand side, we see the electrification adoption. So the main focus on the first will be on transportation. The next will be on the residential and commercial sector actually. So commercial sector and residential sector, it's expected that by 2030 and by 2050 they contribute to electrification actually. So that's the goal, and then this electrification means the amount of demand of electricity that is needed. So now I'm sure that the energy system that we have, or the electricity generation for Ontario, they're looking at these studies and they try to match up with these ones and to make actually available electricity for 2030 and 2050 targets that we are going to achieve for decarbonization actually. Now, let's look at when is the opportunity to install a heat pump in our commercial facility. So if we want to add any cooling to the system, so it's better that to consider heat pump. If we want to replace the existing cooling system, or our cooling system is near to end of its life. So it's better that to consider heat pumps actually. If we want to replace heating system or the heating system is near the end of its life. Is there any questions? Okay. So if our heating system is near end of its life, so then again, it's good to consider a heat pump. And then, facilities with the cold and hot spots that it actually occupants, they have an issue with their comfort. Again, it's good to consider heat pumps to be installed actually. By saying this, now I want to show you a couple of cases. Some of them are from US, some of them from Canada actually, and see that what exists there actually. So this is in Minnesota, and then the design temperature is similar, is even colder than GTA actually. So the design temperature, which means that almost based on the ASHRAE, is minus 28 degrees Celsius. For GTA area, we consider minus 22 degrees Celsius actually. So this area is colder than GTA, but maybe it's similar to northern part of Ontario. They installed a VRF plus a heat recovery actually for that one. And they found in that study actually there is no need to even have an auxiliary or supplemental heating systems actually. And basically they retrofitted the building, and they actually in some places for just the showcase, they installed a light on their thermostat and showing that if the thermostat providing cooling, so then the thermostat becomes blue. If the thermostat showing red, it means that the system is providing heating actually. So, and they showed that at the same time, anyone can set their thermostat, and then they can, every zone, they can, have a comfortable area, and they saw actually, savings in their systems. So it's cold winter zone actually, and it has a hot summers. So it's a good VRF. They installed it, and they reported in Minnesota that this is a good system. The other one that we have, this is in Edmonton, Alberta. So this is an office building. It's a one floor plus a mezzanine. It's around 1,000 square meter or 11,000 square foot facility. The existing system that they had 7 outside condensing unit and 7 indoor furnaces. And then inside the building, they had a ceiling mounted water cooled heat pumps actually, and ceiling furnace for the warehouse actually. They retrofitted with a variable refrigerant flow with a single VRF system with a heat recovery, which included 9 zones and 25 fan coils actually. So basically, when they did that one, this was the before. So you see that these condensing unit outside. But as I said, it's better to consider if we have a space inside of the mechanical room to bring the outdoor unit inside of our building, because they become more efficient for our VRF or heat pumps. And what they did, they add these grills to bring air actually to the system, and basically a 20-ton system made up of 2 10-ton VRF system modules actually. So these are the 2 units that they installed inside of the building. And then that's it. Basically, they added, dampers to the wall of the mechanical room. And this system works perfectly in Edmonton, which is which has a colder climate than, for example, GTA in our cases. The other case that I have, it's a hotel actually. This hotel has 2 main buildings actually. It's 1.5 million square foot, or 100 almost 40,000 square meter. Again, the existing system was a chiller system that they had it for cooling and heating. They replaced it with a VRF system, and what's happened is that the noise actually reduced. So the complaint from the noise that they had, it was reduced. And then they looked at the total installation cost. It was competitive actually. But the good thing is that now it can provide simultaneous heating and cooling. So the guests, every guest suites, they can benefit from this one actually. So basically, each of these systems, they install a 20-ton for heating and cooling systems. And then, they actually could provide almost 1,400 guest suites that they have without doing extra retrofit in the building actually. So if we have a VRF system, the core benefit is it's a modular design. So that's the one benefit. It's a quick and easy to install because it's a brand new building design. It's a really good to consider this one. It's very energy efficient, even in extreme conditions that we might have. And it provides exceptional comfort control because the temperature fluctuation is much less than the conventional system, and all control parameters remain the same that we have that one. So if it's possible, it's better that we consider the heat recovery. So then it provides more efficiency to the system actually. Now, I want to show you a case of the economic of these, electrifying a medium-sized commercial retrofits. So this study was done for different cities in US, but I just picked Chicago because it might be closer climate to us in Southern Ontario, for example. So they said that in the conventional or the baseline system, we have conventional gas rooftop units actually. Then for the second option, they said that if we retrofit that with a heat pump rooftop unit with a gas backup, or option three is the heat pump rooftop unit with electric, backup actually. And then option four is that the heat pump actually rooftop unit with electric resistance backup plus the energy recovery and some other, efficiency measures and so on. So the option 4, 5, 6, basically they consider the same heat pump actually with electric, backup for extreme conditions, but they added more energy efficiency measures to the facility as well. If you look at it, each color shows different cases. For example, case 4, 5, 6 that we look at it, all of them, they have, heat pump with electric resistance actually backup. And you see that all of them, they bring saving to the building owner. If you look at the life cycle, a 20-year of operation of the facility, including the purchase of initial cost, which is in purchase and installation of the system, you see that there are many savings that is available to the commercial building, and it has a positive net present value for these cases actually. It has also, natural gas because we are switching from a fossil fuel burning uh, system to an electricity or electrifying the building. So that's going to be another benefit of switching to these heat pumps. Again, they did not account for that one in their NPV calculation, but if there are, some taxes on the natural gas, that can be also considered and added to the calculation, similar to Canada. The energy recovery that or energy efficiency measures that they considered, that's also good. If we are going to retrofit our heating system inside our commercial buildings, it's better that we take a look at any recovery options that is available to us. And also at the same time, if we can reduce the load by doing any energy efficiency or energy conservation measures, we need to do that one. That's going to help us on the cost of the heat pump and the size of the heat pump that we want to install it. This is a typical 2 days in January operation of different cases actually in a different temperatures. And you see that some cases that if you have a natural gas, for example, so then we need to turn on again the natural gas backup, like case 3. But if you have an electric backup system and you're having a rooftop unit with a heat pump, they are more efficient to work during the cold days actually. So this shows the net present value for these scenario that we had actually, and also on the right hand side it shows the annual greenhouse gas emissions that is going to be reduced. So the yellow ones are the natural gas, burning. Uh, so we are going to reduce that one in the cases that we just switch it to electricity actually. So it's very efficient. It has a 20-year NPV for us actually. And if we combine it with a more energy retrofit measures, it becomes more affordable and valuable for our facility actually. And also, its performance in a cold climate, it's good actually. So there is no question about that actually. The other example that I have is for a strip mall or a low-rise retail as well. So in these cases, we have several tenants, and you typically we have a lower budget, and then we don't want sometimes do a zoning. So each tenant they want to have only one unit and easy to change, because for each unit or each tenant, we just remove the rooftop unit and we install a packaged heat pump actually. So the first cost will be lower actually, and the maintenance it becomes simpler, and the control also becomes a simple control, quick installation, and one unit per one store. That's a good one to be considered. There is a possibility to consider, VAV rooftop units actually versus a constant air volume. So the VAV is a little bit more expensive because it's variable air volume. So then the CFM of air can be different based on the temperature, the air temperature that they want to have in their area actually. But again, its efficiency is much higher, and that's a good one to consider. They are a little bit more expensive than the CAVs, constant air volume RTUs, but it's good to be considered as well. The other example is about the warehouses and storage facilities. Again, in the storage facilities, we have typically a large floor area, and there are many spaces with no people, with or low number of people in them. So then typically we will have an uneven temperature distribution, and then a poor air movement, and so on. So it's better that we use some kind of air distribution through the aisles actually, and then considering economizer and the heat pumps for these facilities. So typically a vertical stacked actually heat pumps are really good for the warehouses. They reduce the installation costs, reduce the operating costs and maintenance, and they have a longer product life as well. So this is good actually, but the first cost can be higher, and it might take some areas inside the warehouse which might be expensive actually to use those areas actually. So again, this is a good solution considering heat pumps for the warehouses and storage facilities actually. But if we consider those stacked, air heat pumps, then we will have air rotation units, which it solves actually indoor thermal environment, and sometimes it can be a simple solution for the warehouses actually. The next example that we have for you today is for an office building. Again, we want to improve the occupant comfort, and we have a rental floor spaces. So each floor they have different, tenants actually in it. So the idea is that we can go with the self-contained units actually. So basically, one per each floor, we can have those units, and these are decentralized mechanical, either in a decentralized mechanical space we can put these systems there, and then a simplified ductwork or piping layout, that's a good one to have it. And then a compartment unit, which it doesn't have any compressor, so then the larger units, but we are going to have a sound there actually if we are going to install it nearby the office area. So if we compare these systems, it's good to take a look at uh, a rooftop unit, a variable refrigerant flow, a compartment unit, or a self-compartment unit, and the chilled beams actually. So the efficiency of the VRF and the chilled beams are the highest, and the other rooftop units and the compartment units, they are going to have a medium efficiency. The first cost, depending on the size of the system, but typically VRF is more expensive actually. The comfort of all of these, heat pumps or variable refrigerant flow is going to be similar. The tenant billing, the good thing is that, we can have the tenant billing with VRF, because then we can put a meter on each floor or on each zone that we have, and then we can have that one. But if we have a compartment unit, then the tenant billing becomes hard actually, or for the hard chill beams as well, it becomes hard. The tenant maintenance actually on the VRF, the self compartment units becomes high and medium. On the other units, it becomes on the like rooftop units is low actually. On the architectural flexibility, again, uh, VRF is a little bit become a medium, which is good actually. And then for the chill beams is going to be from the roof actually. So if we want to select the contractor, the first and the most important one is to look at the manufacturer recommendation. Whatever brand that these contractors they offer to us or designers, it's better that we take a look at the spec sheets and see that what is there and how the installation of the new heat pump equipment should be. So it's really important to take a look at that one. For sure, we need to meet all the local, provincial, municipal, and national codes that is available to us actually. Always check the performance of the units. So COP, EER, HSPF, and SEER. These are at least the four metrics that we need to check. See that how is the performance of the equipment that are offered to us. And also the job site is really important. As I said, typically if we have a mechanical room, it's better that we install the outdoor unit actually. We call it outdoor unit, but inside the mechanical room, and then provide a good amount of airflow from outside. So this will help, from the defrosting of the air source heat pumps, and also it improves the efficiency of the system as well. There are many standards if we consider VRF systems actually. So there are many standards like ASHRAE standard 15 and 34, ASHRAE standard 34 for safety of the refrigerant, and ASHRAE 15 is about the safety standard for refrigerant systems. If we have a residential system that we need to install the VRF, so it's better that we also review these ones for our facilities and make sure that we comply with these ASHRAE standard. But there are many other standards from AHRI or from CSA actually. So then it's better that we review those standards, either is for ground source heat pump or for air source heat pumps. ASHRAE 90.1 also has some numbers about the efficiency of the systems. Again, we need to check those ones and then meet those minimum requirements. And ASHRAE standard 15, when we are going to design a VRF system, basically it says that we need to take these steps that we have actually. So first, we need to check the layout of the system, and then finding the amount of refrigerant that needs to be charged to the system, and then verify the VRF system layout, which is compliant with the standard 15, ASHRAE standard 15, and then we go to room by room and see that if a room is too small, maybe we cannot bring the refrigerant to that room actually. So again, this is really important to comply with the ASHRAE standard if we are going to consider a variable refrigerant flow actually. So that was the slides and contents that we prepared for you for today. Any questions, more than welcome, and let's have a discussion around these topics that was covered today.
Thanks, Sharia. We do have just one question so far that's come through from Alina. You were talking about the net present value, I think, in the Chicago case. Well, what was the discount rate that was used to calculate the NPV? Do you know?
I don't recall it right now. I can check that one and maybe we can add it to the slide later on.
Sure, that sounds good. I'd like to invite anyone else with questions to unmute yourself and have a discussion.
I see a question from Mo. It says that what is the expected service life of a heat pump? Typically, it's 25 years, actually, to 20 to 25 years. That's the expected life of a heat pump. But if it's well maintained, it can go beyond that one actually. And these systems, I mean, the refrigerant or the compressor technology might change actually, which improves the efficiency. But if we buy a more efficient one today, so then for sure, if we maintain it very well, so then we can keep it for a longer time.
Great, thank you. I think this is an important conversation to have as well with all of the net zero targets that Canada has, and even some municipalities have others of their own. A lot of organizations have their ESG targets and net zero plans. So if you do have equipment in a commercial building that's coming near its end of life, this may be your last opportunity really to hit that net zero by 2050. We have a hand raised. Mohammed, did you want to unmute yourself?
Yeah, thank you very much. Nice presentation. I have one question. Do you have analysis compared to different heat pumps by including life cycle assessment or analysis for all technology, especially for VRF? Okay, when you include the refrigerant leakage or change refrigerant or something like that, which can affect on global or environment impact. Do you have a similar comparison between these by including life cycle assessment?
Yeah, there are life cycle assessment done mainly on the residential heat pumps, I would say. And they actually concluded that, yeah, there is no concern about the leakage of the refrigerant if it's done by, you know, I would say special trade actually or contractors that they have a certificate of doing that one. There will be no problem actually. And that's it's going around the market saying that, yeah, this might leak, but it's not like that actually. Usually the leaks, as you said, it happens during the maintenance or repair, not during the normal operation. And during those times, who is working with the system are those, experts or the trades. So if they are trained and they have the right certificate, for sure there will be no issue with that leakage. But there are many studies for the life cycle of the residential heat pumps, not that much for there are some that I presented here, not that much actually for the commercial sector. But if you are interested in those studies, we had two more sessions. One we had yesterday for the public sector, and last week also we have another recording that we did for the residential sector. I encourage you that you just watch those ones. They are, life cycle assessment presented there.
Thank you. There's also some changes in the types of refrigerants that are being used in this technology. It's mainly being led in the US right now, but Canada, I believe, will follow suit. So we're moving to a lower global warming potential, lower environmental impact in the event that leaks do occur.
Exactly. Yeah. Yeah. These days, I mean, we are going to use a more efficient and a low global warming potential refrigerants actually. And then, as Megan said, that more regulation is coming as well to Canada, which banning some of the again extra refrigerants, and then just allowing a certain refrigerant types actually to be used.
Another question came in for warehouse heating. Do you have a recommendation when you would want to use a heat pump versus radiant heaters?
Yeah, it depends. I mean, because if you use a radiant, the radiant is maybe comfortable, but it just is going to be that zone of the radiation under the radiation. Versus if it's okay to move the air through the entire warehouse, so then these vertical stack systems are better compared to the radiant one. Radiant one is typically considered for the area that is more has more traffic of the people or the warehouse occupants, I would say. But again, in these cases, it's better that if you're switching to a heat pump, which is electrifying, because the radiant sometimes they use natural gas, burning system, or even if you want to use direct electricity, that's not good option because the heat pumps are more efficient, I would say, to be used. And then you can move the air if it's okay to move the air, if there is no dust or anything else with the products that is in the warehouse. So the best is that to consider these vertical stacked heat pumps actually, and then you can have the outdoor unit somewhere, and then connected through the refrigerant to these vertical stacked. This idea actually came from the condo towers, because the condo towers they use these vertical stacked a lot actually. So it's good that the warehouses also consider the same technology, which takes the air from the bottom of this vertical stack and then bring it back with a temperature that is desired or at the set point to the facility.
Thanks. Okay, maybe we can move on to the next slide. We've got some closing remarks and information for everybody. Thank you. So I put a link in the chat. We have a post-webinar support intake form. If you feel like you have more questions, you can always email us, or if you need some guidance on a particular project, we work with a number of subject matter experts, just like Shahryar, on all kinds of different technologies, processes, and systems. So this form will actually get you connected with the right kind of expert. We do these virtually as well, and everything is sponsored by Save on Energy, which of course is administered by the IESO, the grid controller in Ontario. You can email us as well at trainingandsupport@ieso.ca. We have a link here where you can sign up for our monthly bulletin. We have a live training calendar online. So you can check on future upcoming events, get yourself registered for those. And then the Save on Energy Training and Support webpage, which I've already put a link in the chat. That's where we upload all of these recordings and the presentation slide decks. We also have a lot of other support resources there. There's a lot of M&V templates. There's some fact sheets about heat pumps. There's information and guidelines. There's a few calculators there as well. So check out that webpage. There's a lot of resources. All of this is provided at no cost by Save on Energy. And then over to the last slide, Shahryar. This is Save on Energy's direct contact. Again, that's the training and support email I just put in the chat, the website that I had put in the chat earlier. And if you want to sign up for Save on Energy's quarterly business newsletters to get their latest information, there's a QR code here for that. You can follow them through social medias. And of course, they offer all kinds of energy efficiency incentive programs, especially for the commercial and industrial sectors. We're finished a little bit early today, but I think we can stick around if there's any last questions.
Yeah, for sure. Yeah, if there are any questions. Yeah, if there are any questions, feel free. We have time. We can go through them.
Yeah. If not, I wish you all a great day.